Hey, I will give you some insights about what Schaeffler is doing with additive manufacturing and the added value we see in production. But first, let me start with some important milestones of Schaeffler and the history. The company was founded after World War II from the Schaeffler brothers, and the first innovation they had was the cage-guided needle bearing. After that, followed some more bearing applications, and they grow the company over decades. They spread to several continents, and after the death of the founder, his son and his wife took over the responsibility and refocused the strategy. We had some acquisitions of Look and FAG, and this led to a much bigger company. And in 2015, there was the IPO of Schaeffler. So we are traded on the stock exchange. And then we refocused a bit on system supplier, and we had some more products, like for the e-mobility, Compact Dynamics was acquired, and some more acquisitions were done in the e-mobility. Autonomous driving was an application, hydrogen is a current topic, and condition monitoring, for example. The company is divided into 3 divisions. We have the automotive technologies, where we offer groundbreaking solutions for almost every car in the world. I think there's no car outside there without a Schaeffler part. But sometimes parts get broken, so we have an automotive aftermarket to supply spare parts, and we offer complex repairs. And the 3rd division is the industrial division, and here we offer products and solutions for the industry of the future. Here's some figures about Schaeffler. We have over 80,000 employees all around the world in 200 locations in 50 countries, and over 80 plants. We made a sales of 15 billion last year, and 6.6 EBIT margin, and over 1,000 patents were registered. The product portfolio is mainly focused on mobility solutions. For example, for cars, for passenger mobility, or for cargo mobility, also railway, airplanes, and so on. And also for the energy sector, we offer also solutions for machineries and transmissions. And to produce these products, we use several production technologies. I don't want to go into detail about the technologies, but all of them have one thing in common, and this is handling of parts, feeding the lines, and a significant amount of automation. And today, we are talking about additive manufacturing in the field of additive manufacturing for automation and handling. And the view on additive manufacturing we have at Schaeffler is shown here. We see the potentials, maybe you saw that in the presentation before, of a digital spare part, where all the information is in the part and saved in a cloud-based solution, for example. And we have new possibilities to design the parts. We can integrate functions to get a benefit of that. And we also can realize, especially in production, some cost-effective or some cost benefits. We have also all around the world, in almost every plant, at least one or more additive manufacturing machine, and this is why we see the benefit for decentralized production, and that makes much easier to reduce the logistics in between all the companies all around the world. We can increase the development speed. We massively use additive manufacturing for prototyping and to reduce the development time, and with that, to reduce the time to market. We also use AM for maintenance issues. We use it for tools or fixtures or so in our production site. Some of them you may see today, and also for spare part deliveries. I mentioned functional prototypes, okay. And we also see the possibilities to use that in a good manner for an efficient production. The fields where we use additive manufacturing at Schaeffler can be divided in 3 fields. Schaeffler offers a multi-material AM machine, which is offered from the special machinery department. And this year we have, or better had, a cooperation with the VDMA here, because Formnext is ending today, where you can see a virtual model of the multi-material AM machine offered by our special machinery department. So if you have some time afterwards, maybe you can go and see the machine virtually. The second field is that we use additive manufacturing for production of products. We, as a Department for Advanced Manufacturing Technologies, develop the AM production, and then we use it for the production of products. And the third field is, and this is why I'm here today, we see a big potential for AM in the field of automation and handling. And for that reason, I have some use cases with me today. Here you can see quite simple parts. They are manufactured in SLS, and they manufactured in laser powder bed fusion, that we have a metal version of the part to reduce the wear, for example. And it looks on the outer shape quite simple, but the task is to transport parts to an assembly line or within the machine. And here we handle cages for bearings, and we use compressed air at the rear side of the part to maybe, you can imagine, spit out the part from the part here and put it into the machine. And we had some issues with conventional manufacturing because we have some internal structures to adapt the airflow, and we simulated the flight path of the part, and we can handle the parts much more carefully than before, and this reduces the damage of the parts, which was higher before, and with that we reduced the scrap rate. Also, a second example from an assembly task. Here we have a component feeder, which is manufactured by selective laser sintering. The task here is that we feed balls from a roller bearing to an assembly line. And the aim here is to realize a quite compact design to feed 2 balls at the same time, where we can reduce the cycle time with that. And you can imagine, if you want to mill this part, this would be quite complex. Here we have just one part, so we have a part integration, and we reduce all the machining operations or the designs to assemble the single parts. And the most important benefit is that we have a cost benefit of around 50% compared to the traditional approach if we would use it. And finally, we are much faster in production because we can here feed 2 parts in a row. Third use case is from grinding. Grinding is a very crucial process when you produce bearings, because every bearing ring is grinded. And therefore, we see a huge potential to use additive manufacturing to design the cooling nozzles, because coolant is obligatory for grinding, and you have to transport the cooling medium to the grinding tool. And here we also used a simulation-based approach to design the nozzles inside. So the IP is inside the part, but I cannot show that. We have a much more efficient cooling, and with that we can reduce the cycle time up to 20%, which is quite a lot when you think in euros. We reduced the setup time up to 20% because we can design the interface to the surrounding infrastructure, which is much easier to handle and to adapt. And you have just one position to align the nozzle when you switch the tools. So we are faster also here. And we realized a much more efficient cooling. And with that, we can reduce the coolant amount up to 80%. And when we think on sustainability, this is quite a lot because we can also reduce the pump in the machine. So we have less coolant and we have less energy needed. So energy savings are around up to 20%. And all in all, we saved several 10,000 euros just with one nozzle in one machine. And when you imagine that we have several grinding machines, you can see the big potential when we adapt the cooling nozzles here. But not every AM part, in my opinion, must be simulated and all the benefits must be taken from the design. But when I show you some example from our colleagues in Skalica, Slovakia, they use massively fused filament fabrication because they think, or their approach is to keep it simple and to be faster in the part delivery than the conventional approach from milling or so. So they massively use fused filament fabrication, and a summary of what they are doing is shown here in the video. You see we have guiding and orientation issues, grinding, okay, they use plastic nozzles, also optimized here. We have some Poka-yoke applications to sort parts in a quite short time and to sort them out. Handling grippers, I guess you saw that today a lot when it comes to handling. We have also some fasteners, for example here, for safety moving. All integrated in the production line to sort the parts. Also moving is implemented here. And you can imagine that they just print the parts and they have to fulfill the accuracy. There's no milling afterwards. They have to fit. They just put it in the machine and it has to run. So they won't simply reduce the downtime. So all in all, they are much faster. They have shorter lead time compared to the conventional approach as milling. They completely reduce the raw material supply, and they increase the part availability. Sure, they print only what they need, and all in all, they had a lot of cost savings. Only 2 employees with, I guess, around 10 printers supply all the parts for the plant. And they had around 10,000 euros per year savings just to be faster, and it works also. So let me sum up a bit what we see here. We have 4 main drivers. We have the availability, we have shorter delivery time, we print on demand, and this means we reduce the stocks. We have the possibility to design the parts how we need them. We have higher efficiency by using the AM design, as you see for the cooling nozzle for grinding. We can adapt the part geometry. When a part gets broken in the line, then we can adjust that. Also an important issue. We have the flexibility to adapt the design for changing conditions. We have several variants of products running through a single line, so we can adapt the grippers also much easily. And finally, the productivity increases when we use the benefits of AM. So that was a quite short and quite quick overview of what we are doing. So if you have some questions, don't hesitate to ask me or contact me via LinkedIn. You are more than welcome. Thank you.
Thank you, Thomas.